All right, welcome to our 7th video of our 5th unit of AP Chem. Calorimetry continued. We are actually going to start performing calorimetry, or at least solving problems like what we would do if we were doing calorimetry in this video. So, the heat capacity is the amount of heat required to raise a substance temperature by 1 Kelvin. So the higher the heat capacity of a subject or an object, the more energy is needed to raise its temperature. Heat capacities are why sometimes if you're eating pizza, you may be able to hold the pizza by itself with the crust, but as you bite in, the sauce is suddenly really hot. That's because the sauce has a different heat capacity than the crust, for example. The molar heat capacity, denoted by C with a lowercase m, is the amount of heat required to raise 1 mole of a substance by 1 Kelvin. So the molar heat capacity is basically the heat capacity of 1 mole. Keep in mind, raising by 1 Kelvin. The specific heat capacity, with an S, is very similar to molar heat capacity, except it is the heat required to raise 1 gram of a substance by 1 Kelvin. For example, with water, the specific heat capacity is 4.18 joules per gram times Kelvin. Specifically, it is actually 4.184, which hopefully you remember is how many joules there are in 1 calorie. So, just kind of random trivia. There you go. The 3 most common equations we use in calorimetry are going to be following. I'm going to show you the equations, and then basically we're just going to kind of relate them. To begin with, Q equals M times C with our specific heat capacity times delta T. This says that the heat required is going to depend on the mass of an object, its heat capacity, and how high you want to raise the temperature. Okay? You multiply them together and you'll figure out how much heat you need to raise that mass with that heat capacity by that many degrees. Delta T typically is measured in either Kelvin or Celsius, but if delta T is 13, that can be both Celsius or Kelvin, meaning a difference in Celsius is the same difference in Kelvin. They will end up obviously in different temperatures since you have that 273 difference, but a 13 degree of Celsius change is the same as a 13 Kelvin change. Our second equation is Q equals N times Cm times delta T. It's the exact same as the first equation, except instead of mass we have moles, and instead of specific heat capacity we have our molar heat capacity. Exact same setup. It's still based on the amount that you have times its capacity times however much you actually want to raise its temperature by. But, yep. All right. And lastly, in case you're given specific heat capacity or molar heat and you need the other, your molar is just your specific heat times the molar mass of that substance. And that's it. Those are your 3 most common equations. We will use them very often in calorimetry, for example, in our next example. So, a 0.5865 gram sample of lactic acid, that's the molar mass, is burned in a calorimeter whose heat capacity is that. Temperature increases from 23.10 degrees Celsius to 24.9 degrees Celsius. Calculate the heat of combustion of lactic acid per gram and per mole. Most of the time, to begin with, their heat capacity is 4.812 kilojoules per degree Celsius. Okay, so this problem is a little bit different than most calorimetry problems you're going to see, which is honestly kind of why we're doing it. Typically, all you do in a calorimetry problem is you have Q equals M times CS times delta T. And basically, they will give you Q or M or CS or delta T, and you find the other 3. However, in this case, it requires you knowing a little bit more information. They gave us the heat capacity, but they don't specify whether it's specific or molar. So we have to solve this a little bit different way. First off, our heat capacity allows us to convert between kilojoules and degrees Celsius. Now, we do know our degrees Celsius change, and what that says is we can figure out how many joules were required to actually raise that calorimeter by that degree Celsius. Then what we can do is assume that if that many joules were what were released, then we can figure out how many joules that came per gram, and also using the molar mass, how many came per mole. So again, a little bit different, but basically kind of the hard version of what you're going to be seeing. So first off, we got to figure out our joules. So our Q in this case will equal our 4.182 or 812 kilojoules per degree Celsius, and we're going to times that by our temperature change, which we've got 24.95 minus 23.10. That gets you 1.35. Okay, put a little point there. You multiply those together, and you get 6.50 kilojoules. That says that when we reacted this many grams of lactic acid, we produced this much heat. Now we got to figure out, though, how much of that heat came per gram and how much of that heat came per mole. So first off, per gram is just going to be 6.50 kilojoules per 0.5865 grams. When you multiply that out, you get 1.08 kilojoules per gram. And then we have an equation where we know that our molar heat capacity is equal to our specific times our molar mass. The molar mass of lactic acid is about 90.09. Our specific heat capacity that we're kind of working with is kilojoules per Kelvin. I know it's not technically heat capacity necessarily, since we don't have a degree Celsius, but it'll work. I'm sorry, it's not kilojoules per gram. It's 11.08. Anyways, you multiply those together, and you get that our molar version is 998.20. So again, we figured out how they didn't give us per gram, so we had to figure out how much the total reaction gave us. Then we could figure out, well, how many did we get per gram, and also how many did we get per mole. We got per mole by converting from grams to mole using this equation. There you go. That is how you do kind of the hard version of calorimetry. I'll do another example, actually. I know it's not in your notes, but this way you get an idea of what the typical ones tend to look like. All right, so that's a white background because I just had to add it in. Sorry. Some of you may actually be able to read it better. Anyways, so how many joules are required to raise 390 grams of a substance from 34 Kelvin to 67 Kelvin if its specific heat capacity is that? Well, our equation basically is Q equals M CS delta T. Okay, the entire hard part of this equation is figuring out what numbers go with actual what variables. Well, when I said the hard part, I lied because that's not hard. Okay, we are looking for joules. Joules, hopefully remember, are measured in Q. That means that we are trying to solve, for this one. That means all these others should pretty much be filled in for us. Well, they told us our mass, that's 390 grams. Our specific heat capacity, they told us, and our delta T, they told us. If, for example, they had given us molar mass or molar heat capacity, we can convert. Typically what you do is you base which equation you used off your heat capacity. So if they gave you moles, if they gave you molar heat capacity, put everything in moles. If they gave you specific heat, put everything in grams. Kind of an easy example for us. It was a quick one, but here you go. So our Q then is going to equal 390 times 8.32 joules per grams Kelvin times our delta T, which will be 67 minus 34, which is 33 Kelvin. Notice our units cancel out. We're left with joules. Thus, when you multiply them together, you get a ridiculously huge number, because I picked random numbers, of 107,000. So that's typically how equations go. Sometimes they'll ask you to solve for mass and then give you everything else. Well, use your algebra powers, you can do this. Sometimes they'll ask you for final temperature, they'll give you initial. We'll solve for the change and add it to your initial. Most of this just comes kind of down to algebra. You should not be stuck on this. If you are, come talk to me. It won't get easier. However, it doesn't get drastically harder either. With that, thanks for watching.